Okay, so first, a few words about what we do with my group. So human robotics. Yeah, so we use robotics as a tool to investigate human motor control, human sensory motor control. So for example, these people with 6 fingers to understand whether how they can manipulate. So we found that they are more intelligent than us in the sense that they can manipulate, they can provide manipulation better than we can with 5 fingers. I think you may hear about that more with the presentation of Carsten Mehring on Thursday. We use robotics to help humans, so this is a goal. So, so for example, this guy who has cerebral palsy, so his hand is trembling widely, and so he cannot use a conventional motorized wheelchair. So the goal was to provide an interface to this guy so that he can move safely and as much as possible as he wants. And also when you design an interface like that, you have to make in a way that for people who are not impaired, it should not change anything to the normal wheelchair. And so that's what we did. So this is what we do. So where I'm from, so I grew up in Switzerland. I did studies there. After I was for the postdoc in Canada, USA, and Japan. And after I was 5 years in Singapore and after in the UK. And these are some of the people along the way with whom we collaborate, and some of them I will show the results. So, okay, so my presentation will be to try to look at this question. So is it better to have 3 hands like this guy? So this is an art vision, but actually some neurological patients, they think they have a third arm. And so is that better to have a third arm, or is that better to work together with a partner? And so let's look at augmentation in general. So the goal, so of course you have pathological people and arts, but the goal would be to make something that is useful. So for example, so if you have to work alone, and so you have to hold something and work on it, then it would be useful to have this augmentation. Actually, the first beyond the comics, the first real implementation of augmentation was done by an artist. So in about 1970, 1980, and Stellark, he developed this vision, and you see that he's writing at the same time with these 3 arms. I find it's interesting to see that it has started from comics and arts and coming to technology at the end. The real use, so something that is probably very useful is for surgery, where you have to you have normally to collaborate with a surgeon. So when you see, so if you see this guy, then you see that, so this guy normally, so you have, so if you see the Da Vinci robot, for example, so the Da Vinci robot, you have 4 arms, and 2 arms are commanded by a surgeon under the console, and the other 2 arms are not commanded by him, but you often have an assistant by the patient to deal with the other 2 arms, and it doesn't seem to be very functional, right? And in fact, when you observe a surgeon, a surgeon and the assistant doing an operation, you see that they have a lot of miscommunication, a lot of ambiguity that has to be solved along the way. And so if you would be able to work all by yourself, that may be better. Okay, so first, robotic implementation were done by, especially by Asada at MIT, the group of Asada. Now, you have the impression everything is working well, but in fact, and according to what the user wants, but in fact, what is happening is that uh, the behavior of the robot is fully automatic. So it's not something that the user is really commanding. Of course, we have the illusion it is, but it's not. So there are still a lot of stuff along the way to make it really useful. So we looked at how can human use supernumerary robotic limb and what are the limits of the human central nervous system to command more than two arms. So the kind of thing you have technically, so you have feedback devices, so for example, a stimulator, for example, tactile or electric with electrical stimulation. You have interfaces, so this can be muscle interface as is dealt especially in this project, from what I understand. You can have, in principle, also brain interfaces, um, but so far the most accurate use or the most control we can have with so-called body interfaces. So typically, if you sit, you can use your feet to command additional robots. So like quite a few surgeons, for example. So this is something that can be used, and normally, of course, you have the control, you have the feedback already on the foot. So this is something that seems to be working well. Now, we had to do a lot of experiment to understand whether you can really control more than your arm. And so we did quite a few experiments where so you sit, you can use your feet, you can use your hands, and you have either virtual tasks on a monitor with 3 or 4 actuators, or you have a robot or 2 robots that you command together with your hands. And I want to show you one of these study. So one thing that is important, so if you want augmentation to be useful, then it should be able to complete tasks that you cannot do alone with your 2 hands, right? Because so it has to add something, and it has to add something in a way that the performance are satisfying. And as a benchmark, we make that the performance should be as good as if you do the task with somebody else. Okay, so this is an experiment that we did. So you have an elastic triangle. So it's basically a triangle between my 2 hands and 1 foot, right? And what is interesting with this elastic triangle is that you have to control both the position and the force. And it's a bit similar to what surgeons have when they have to, so for example, when you want to make a suture, then you have to pull the skin and work on it. So you have to control the skin elasticity. Okay, so this is this task on a monitor. So you have this operator. So you have 2 haptic interfaces for the hand, and you have a special foot interface, a dedicated foot interface that has haptic feedback, so that you know where your foot is without having to look at. And actually, that's the current state. So in surgical robots, you have primitive hand interface in terms of button. And what you see is that often the surgeon has to look what the foot is doing. And so if you give haptic feedback, the surgeon will understand where where his foot is without that. Okay, so we did compare two different population of subjects. So one, you have the solo configuration. So you do all by yourself with the foot, the hand and the foot. And in the dyad configuration, So you do this with two people, and one has a foot and the other has the hand. Okay, so we distributed 1 hour of training over 3 days. So on the first day, you have familiarization, then you test the performance at the beginning, then you have one training. On the second day, you have 2 sessions of training, and on the third day, you have a session of training and the final test. Okay, and these are some of the results. So you see that the success rate is plateauing with this last 2 sessions, and the time is decreasing and also plateauing more or less. So that this training would be sufficient. Now, if we look at the success rate, so you have to transform this triangle from one place to the other to a third, etc. Then this is very interesting. So if you look at the first day, you see that the dyad is much better than the solo, right? So that's the first day. By the end of the third day, you see that the performance are similar between the two conditions. Similar for the time, on the first day, the dyad is faster, the dyad performance is faster. At the third day, it looks like the solo performance is a bit faster or the same statistically. Okay, so then it seems that the performance are as good or even better when you work alone with these short trainings than if you work with a partner. Now let's look, so we did a questionnaire to understand whether they like, whether they would find comfortable, etc. So one question is on the difficulty. So the first day, you see that the solo operation seemed to be very difficult, more difficult than the diet condition. On the third day, you don't have this difference anymore. When we look at the preference, so which condition did you prefer? The first day, they don't like the solo operation. The third day, they prefer the solo operation. So from that point of view, it seems that this experiment shows that this trimanipulation is fulfilling these necessary conditions. So we get with 1 hour of training, performance and preference similar or better in solo than working together with somebody. This is an experiment we did doing so we had a European project called NIMA, also with people from here. And so one partner was Nathaniel Jarassi at Sorbonne, and they have an actual backpack with a supernumerary arm, and we did operation with them. So we tested systematically different kind of operation with trimanipulation. So looking at the number of targets, so whether you have 3 targets independently, like in this case, or whether it's all connected, so if you have an elastic triangle. And we looked also at the mechanical connection, so whether it is uncoupled, so here the 3 arms are totally independent, they can move independently, and when they are mechanically coupled, so in this case, again, with this elastic triangle, then they are fully coupled. So this is a taxonomy of all possible tasks based on this number of targets and this number of mechanical coupling. So we did a study with that. So basically, again, we found that solo operation is about as good as with another person, a bit better. Now, these are really preliminary results because it's actually very difficult to, so if you have a robot arm, you have the limitation of the robot. So the robot is very limited so far, and so I wouldn't say that it is a final word on that. So we have to work with better robot, better control to be able to answer the question fully. But basically, so from all the studies we have done, it seems like that it's not a problem to have 3 or even 4 arms. This is not a problem at all, as long as you have only one task. You cannot have different tasks at the same time. So basically, to me, my understanding is that I cannot play chess against myself. So if I have tried actually, and it's not very successful. At some point, you have to choose which one you want to win. And so you have to concentrate on one. And it seems to be the same here. So you can have 2, 3, 4, maybe more limb as long as it is on your brain understand as one action. Okay, so now, let's look at the work that Yan Pei did. So she was a PhD student also with me. I mean, I was co-supervising at NTU in Singapore, and after she came for the postdoc here, doing this NEMA project. And first, she developed this haptic interface I told you about. So this is a passive interface, so without actuators. We wanted it to be passive, to be more simple. And actually, so when you make it passive, you don't have the problem of the actuators. And so the principle we have is that we have spring against force tensor. So it's good because you feel the force with the foot, and you also feel the displacement. And we could make experiment to show that when you feel only the force, then it's uncomfortable. You have really to feel the two, so force and displacement, to have a good experience. And the displacement can be small, this doesn't matter, but you should have some displacement so that you feel comfortable and can learn better. Anyway, so this is for a sitting person. You have to consider, so if you sit, so if you have to do that, you cannot make long. So it's important that your foot is on the ground. Another thing is, so we developed this interface and we extracted individual motion patterns. So each of us has slightly different motion pattern, and so it's important to identify individual motion pattern using machine learning techniques. And so in that case, we could show that you get better control and more intuitive. One of the applications she did is for endoscopy. So this is what you have normally. So you have the surgeon, and you have an endoscopist by the patient, right? And what we would like to do is that this endoscopist is coming to the foot. Okay, so this is the implementation. So you see that you can control with the foot, you can control this soft endoscope. So this is an innovative surgical robot. So you have an endoscope and you have 2 tools at the end of the endoscope. So you see that. So, and it's so then with the foot, you control the endoscope, and with the 2 hands, you control the two tools. And it's very intuitive, right? So you can think it's like if you would control a drone with a foot. So you control the drone flying, and on the drone, you have 2 robotic arms making some bimanual operation. And that would be like that. So it's very intuitive. Of course, we looked at the mapping actually, so not any combination of foot and hand is intuitive. You have to see which combination are more intuitive. So this is a setup that we have downstairs. I don't know whether some of you know it. Of course, I don't know whether there is a visit of the lab this week, so probably you will see it. By the way, if you want a demo, it could be possible to combine here. We can discuss this later. So basically, what we have is, so you have motion capture. So you have motion capture so that you can catch the movement of a human. And then you have 3D VR here, and you have a treadmill, so a split treadmill, so that it can be faster on one side. If you want to, for example, if you have people who have asymmetry, they cannot work well on one side, so you can train that. And so this treadmill can be oriented, can be also moving sideways. And you have these two green robots that are to make any dynamic interactions. For example, if you want to test the stability of people, you can push systematically, right? So, and you can also make interaction with the hands. So for example, if you want to train full body rehabilitation where you have to place boxes or to test ergonomic strategies, that's something so you can give any dynamic interaction with that. And we have the possibility also to have up to 4 supernumerary arms. And voila, it's not that we will use everything at the same time, but everything is synchronized so that if you need to an experiment needing any of these equipment, then it's already synchronized. You can start right away with the experiment. And yeah, so we have done a more portable interface because so these robots are 8 kilo each, what is already the smallest that you find on conventional robot. But we found robotic arms that are 4 kilo, and so the whole setup here is about 10 kilos, so that you can you are not confined to support the gravity. You can walk almost normally. Yes, application. So next weekend, when you go to the ISS and you want to do some to fix some things there, then you can do it all by yourself. And surgery is really something that is interesting because, again, the communication between the surgeon and assistant is something that is difficult and that has to be relearned with each new assistant. So conversely, if you learn to work with yourself, with your supernumerary robotic limbs, then you need to do it only once and it's done. Some fun. So we had workshop on augmentation, robotic augmentation, and this guy who is Professor Asada from MIT, and he has pioneered the physical robotic limb. So we had a workshop first in London in 2023, and at evening after the workshop, Asada was enthusiastic, especially with the beer, of course. And then he told, okay, the next time we do a workshop and we make a fashion show with augmentation. So that's what we did in Yokohama. Okay, so this robotic movement augmentation is full of open questions. So I would say just starting. One fundamental question is whether we can add degrees of freedom that are commanded independently from all our other degrees of freedom. Is that possible with some neural interface? So we have done, so within NEVA, we have done some investigation with motor unit interface. So we have found some interesting things. For example, Haim will speak about that, I think, during this week. Now, it's not that you have really the good real-time control of a robot that we would expect. But what we know is basically, so if you use just a muscle interface or a motor unit interface, probably you don't have sufficient control. Now, there are other, so on the other hand, if you use an implant, then probably you are able to add degrees of freedom. Of course, it's not something that we can do on us just like that, right? But so whether we can really add independent control of degrees of freedom is still a bit open. We know that it is hardly possible with muscle interface, but we have to see with other kind of neural interfaces. The critical aspect is how to provide sensory feedback, because, of course, I mean, you have sensory feedback. It's not that you can find areas where you don't have feedback. So you have competition with natural signal. Now, another question is how to learn to control supernumerary degrees of freedom, because, yeah, so for example, children learn to walk, but it takes a long time, right? It takes them to fall many times. And so if you want to control a supernumerary arm, probably you cannot offer such a long learning. So you have to think about what is possible, what is working, and also what is practically possible. What we want to work is on integrating autonomous behaviors, and in a way that I could use an autonomous behavior and switch to voluntary control at will, right? So that's something we do. So for example, if you break your leg, then you have rehabilitation. And at the beginning, you have really to think hard about what you do. But after it's become automatic. So that's something that we should try to recreate for supernumerary robotic arm. And yeah, so another thing is, of course, application for surgery, for maintenance, for cobot, etc. Now, so this was about adding a robotic supernumerary arm, so a third arm, etc. Now let's think about sensory aspects. So when, for example, when you have two people moving a piano, then you don't actually need to speak much to do that, right? So you may specify that we take this door or that door, but other than that, you would normally understand. And if you want to do this with a humanoid robot, much more complicated, right? So what should you communicate? So you should say, okay, so you need to move 5 cm to the right. What is 5 cm? What is right? And you don't want to have to communicate every millisecond, right? So somehow humans have a better way. And so we wanted to understand that. So we have a dedicated robotic interface. So for example, this one that you may see when you visit the lab. So basically, so you have a robot, so one-off robot just for the wrist flexion extension. So you have also one-off robot here. And you can make for two people, you can separate them with a curtain. So using this interface, we did quite a few studies. So I want first to show you a study that was just completed by Dorian, who is postdoc in my group now. So the question is, we want to understand how people communicate the timing of the movement, because so if I do movement, so point-to-point movement to take the bottle, for example, and if any of you is doing the same, we will have different timing. I will have my timing, and you have your timing, and this timing is something that is valid not only for reaching, but also for walking. So you have people who are faster, systematically faster than the average, and you have people who are systematically slower than the average, and of course you have people who are just at the average. And so we wanted to understand how this combine, right? Because a priori, so you have one person who is faster than another. How do they make that they can work together? So that's the experiment that Dorian did. So you have point-to-point movements. So you start here and you go to any of these targets. And you have a connection with an elastic band. And were some of you subject of this experiment? Were you a subject of this? Okay. Anybody else? No. Okay. Okay, so this is performance when you are not connected. So you have the position, you have the velocity to this different target. Of course, when you have a longer movement, it's taking more time, nothing surprising. You have some sub-movements, so you don't go very smoothly at the end of the movement. And that's what I told you. So you see that the time, okay, the time is longer for a longer movement, of course. Now you see that some people are systematically slower or faster than the average, right? So that's something that is known, that has been documented again on walking, for example, also, etc. So this is, so you can quantify this systematic tendency to be faster or slower by something that is called vigor, right? It's how much effort an individual is prone to exert to make an action. Because when you do the action faster, you will need more energy, right? Okay, so now we connected the people. We want first to understand whether they have independent motor plans, so whether they communicate at all. So we do simulation for that. So if you have one who is faster than the others, then you will have problem by the end of the movement because one will be at the end when the other is still on the way, right? When we do experiment, we see that there is nothing like no evidence that they have problem to communicate or that they don't communicate because, in fact, the movement are smoother than when they do it alone. They are smoother. So then from that, it seems that the two subjects have coordinated motion plan. So they somehow understand what timings they want to take in their movement. And so something that is interesting, so we consider, of course, when you have two people connected, one is faster than the other, yeah, or the same speed, but normally one is faster than the other. So we group all the faster of all these dyad together and all the slower of all these silent together. And we consider these two groups. And what we see is that when they are connected, basically they save time, right? Especially, of course, the slower we win more time, of course, that's logical. But even the faster go faster when they are connected, right? And again, so if we consider the timing, so now we know that this dyad communicates, so communicate to find a common motion plan, then we see that the timing of this dyad is also increasing with amplitude. And again, you have that some dyads are faster and some dyads slower systematically. It's not that they are faster for one and slower for another amplitude. Okay, so from that we can define a vigor for the dyad. And another thing that is interesting, so you have the people who are first making the movement alone. After you connect them, after you test whether the practice of moving together influence their own behavior. Then you test without connection at the end. And what you find is that basically, so the faster people keep about the same speed that they had before, and the slower people take the speed of the faster. Okay, now we did a model that I will not show here. So Dorian did a model, and it seems that, okay, so the slower become as fast as the faster, that one thing, but actually the way they change their movements depend on the slower. The slower is determining how the two change their arm behavior. Okay, so from that, so we see that in this very primitive movement, so where you could actually do everything open loop, right, without really coordinating, we see that at least trial after trial, they have some communication and they find some compromise, they find a common motion plan. Now, we did an action that requires much more feedback. So basically, we had a randomly moving targets, and we have these two people who are connected again with two robots. So this one is with his robot, this one is with his robot, and you can connect the two robots as you want. For example, you can make that one is connected to the other, but the other is not connected to the one, or the two are connected together, or no connection at all. And you see that they see each other, but they don't see, I cannot see your hand, right? But I can see that you are in the room, so they enter at the same time in the room. And this is a task. So you have this web target that is moving randomly, right? And they have to track with a hand movement. And both of them have the same web target, right? They don't know that, but they have the same task. And in some trial, they are connected with a spring force. So it's like, so of course it's coming to the robot, but it's like if my hand is connected to your hand with an elastic band here. Okay, and the elastic band is giving just haptic feedback about where you are going, but it's not strong enough to guide the movement. Okay, so now at the end, so sometimes they are connected, sometimes they are not connected, not connected, etc. So after about 60 trials, we ask them, what was that force? They have no idea. So on 80 subjects for the first experiment, only 2 of them found out that they were connected. Some they say, oh yes, I know, you connected me to my previous trial, what is completely different, of course, because no real-time interaction. And we ask them, so does it help this force that you feel, or does it disturb you? It's disturbing all of them. But that's what they think, but in fact, it is helping them. So we can see that. So if we look at the improvement of tracking error, so we measure the tracking error when you are connected minus the tracking error when you are not connected, okay? And we put as a function of the relative tracking error, so I measure the performance of the two people alone, and so if the partner is better, it will be on this side. If the partner is worse, it will be on this side. And what do we see? We see that, so if the partner is better, then I improve. I win from that. Quite logical, right? I mean, if you are with a better partner, logical that you can win from that. What is more surprising is that if the partner is worse, then I also win. And why it is really surprising is that if you take what you have with normal training robots, so if the robot is better, you win. If the robot has no good sensing, for example, you lose. So this is kind of a zero-sum game, right? But in this case, when you have two humans, you win all the time. So this is something very strange. So because this is something very strange and we wanted to understand how it is working, so that's what Takagi Atsushi did during his PhD. So first we tested, Okay, so we tested the mechanical connection, the effect of the mechanical connection. So very simple. So you take an agent, a linear model, another agent, a linear model, you put a mechanical connection, and you simulate the task. And when you do that, you find something that is, so performance is decreasing, so that when the partner is less good, then you would tend to lose. And this is something very different in the behavior from the data, where you do not lose when you're connected to even to a worse partner. Okay, so from that, this means that the mechanical connection is not enough. Okay, so mechanical connection is not enough, then it must have something with something cognitive. It must have some cognitive aspect so that some kind of brain-to-brain communication, or maybe not quite, but I mean, some things that they understand from the partner. And so we tested different hypotheses. And one is that okay, so if I'm connected with you, then your brain understands that we have the same task, and so your brain tries to understand my motion plan and can use it. And the same for me. So I'm connected, so my brain tries to understand your motion plan, and then it would be like if the two subjects have the two pairs of eyes. So I have my eyes and your eyes. And if I have two pairs of eyes, then normally I could do more. So it's like if you have two cameras, you can maybe become more accurate. So we tested that in simulation first, and then on a robot. So you make that the robot is interacting with a human and inferring the motion plan of the human, right? And when we do that, we find that the interaction with a robotic partner is the same, get the same performance as interaction with a human partner. From that, it's strong evidence that when humans work together, then they do not understand anything consciously, but their brain understands that it is the same action, and their brain is making a model of the partner and extracting this motion plan. And from this motion plan, I can combine with my motion plan and become more accurate. So this is a model. So we a study that Katja did is that she looked at whether we are aware of this robotic partner in a different way than interaction with a human. So, it's kind of Turing test. So, this Turing test. So this is basically, so you interact with a computer, and you have to tell whether the computer is a computer or a human, okay? And this is something similar here. So basically, so you have the human subject, and the human subject is connected to either a human or the robotic partner, or this trajectory guidance that is a strategy that is normally used in training robots. Okay, so we have the same task as usual. So you have this. So it's in this one DOF in this case. So it's moving like that, and you have to track, and it's moving randomly. And what we found is that, so we did performance and questionnaire. So basically, the subject recognized trajectory guidance very clearly. They say this is a robot, okay? Now, they are not able to make difference between these two. So for them, whether it's connected with a human or connected with this robotic partner, they don't feel it's different. And something strange, they prefer to work with a trajectory guidance. They don't like to work with a human. And that's something actually that was also observed in other human-robot interaction experiments from other group. And the key is probably that when you interact with a stupid robot, you understand what this stupid robot is doing. And so they like that it's totally reliable, totally predictable, etc. When you work with a human, on the other hand, it's not always predictable. So that makes them a bit more problem. Okay, so does it mean that trajectory guidance is better? So for that, we have to look at the long-term learning, right? So Katja did another experiment. So you had subjects who do, so they train either without interaction or with a robotic partner or with a human partner or with trajectory guidance. So you have 4 population of subjects, right? And then, so you train, then you test on the same day. Then you test 1 day later, then you test 1 week later, okay? You learn only the first day. So you learn the first day, you test. Then you test the next day, and then you test 1 week later, okay? And then, so these are some of the results, and what we do is we compare the error on the first day, the very beginning, and 1 week later, okay? So this is for the solo. You see that basically so this is on the first day, and this is 1 week later. And you see that you keep about the same performance, right? This is retention. And now what you see is that interaction with a human is a little bit better. And with the robot, actually, so when we do statistic, we find also a little bit better. And trajectory guidance is much worse, right? So this is the retention where we test on the same trajectory. So we learn on a trajectory, we test after 1 week on the same trajectory. Now, if we want to look the kind of journeyization, so we look at another trajectory. So we learn on one trajectory and we test 1 week later on a similar but different trajectory. And what we find is that we get, of course, you have deterioration of the performance, but you have the same systematics in the sense that so interaction with a human is improving a bit. With a robotic partner is also improving a bit, and trajectory guidance is really bad. So it means that, so working with trajectory guidance, people like it, but it's not useful. It's not useful for learning. And what is happening is that basically people learn another strategy. So they learn to relax because the robot is guiding you, so you relax. But they don't learn the task. And it's only when you do yourself, or even a little bit better when you do with somebody else, that you get better learning. And of course, this is something important. So when you make a training system, first you should really not use trajectory guidance. Also, it is a strategy that is used in most cases now, but you should not. And now, so it's if the patient can, the patient could train alone or train with some robotic partner or with a human partner so that you learn doing the task by yourself better. Okay, so a bit further on this haptic communication. So Atsushi looked at how people do when they work together, not only 2 people, but more than 2. And so what I thought is that when you are more than 2 people, it would be worse, okay, because they would fight. And so what happens is that, so Atsushi wanted to go to a lab in Japan So he organized everything. He found the money, everything. I had just to sign. Wonderful. And then we discussed with a colleague in Tokyo, and what can we do? And it happens that they had 4 haptic interfaces. So we decided to make 2, okay, so group of 2, group of 3, group of 4, and compare. And this is something that people had asked me about. So when I was presenting the result, people were asking, okay, but what happens with more? And I thought it's not very interesting question, but in fact, it happens that it is an interesting question. Okay, so this is performance to people. So that's what we have seen before. So you see that, so you win with a better partner and you do not lose statistically with a worse partner. So you will say, yeah, but you do not win, right? So before it was something like that. The point is that Atsushi put a lot of visual noise so that you get people with different skills. So that is brings the performance down systematically. Anyway, we have the same nonlinear characteristic, right, as before. When we have more subjects, we thought, okay, the bigger the group, maybe I will win with a good group, right? But I will lose more with a bad group. That's what we thought. Now, what we found is that, so you win more with a big group, right? You effectively win more. The larger the group, the more you win. And now you never lose, okay? So you win more, and that's something that is actually interesting, because why do you win more? You win more because of information. So you have the same exchange of information with the people, but now on the top of that, you have also a mechanical averaging. And because of these 2 effects, you find that when the group is bigger, this mechanical averaging makes that you win a bit more. What is interesting is that, so if you have a bad guy in the group, it doesn't matter. It doesn't disturb, right? So that's something interesting, because then you could think, okay, so I can make training. So for example, for physical therapy, if you have one physical therapist who is good and 10 patients, it doesn't matter that the patients are bad or that one is especially bad. They will still be able to have a good model, so be able to learn the task well. Now, another thing that we also didn't know is, okay, so if I have a larger group, we thought, okay, so maybe I ask you, so if you have a larger group, do you need longer to learn? So who thinks if you have a larger group, you need longer? Okay. Who think you need less time? Who think same? Okay. So I thought it would be longer. So you have, that's interesting. That's the beginning, right? The beginning, you have the same, then just the mechanical interaction, because in fact, you don't know about the partner. You cannot know about the partner. But still, soon, very soon, you adapt. So in about 10 seconds, you learn about the partner, you learn the motion plan, and you can use it, right? Okay, so now what happens with 2 or 4, with 3 or 4 people? So you see that basically RS1, right? Yeah. So basically, you learn at about the same speed, whether you are connected with 1 or more people. Okay, another thing that we looked at, so whether children also already have haptic communication, right? So is that something that we learn when we go, or is that something that we have at the very beginning? It's not clear. So we did experiments with children from 5. Of course, that's very difficult to make experiment with children. Say, don't do what you want, right? Adult also not, but you don't know. But children, you know. So what do you do to adapt the experiment? So you make Mickeys, right? That's one thing. You make Mickeys. And you make, of course, you should make shorter. So for example, now you are really starting to sleep, but if you would be children, you would be sleeping already before or be out of the womb, right? And so you make shorter connection, shorter session. You make so you make ping pong, snack, etc. So you make all this, but still it was not working. I mean, some children would just not do it, and then we changed one thing. One thing is to put a proper reward, right? Of course, it's logical, but it is like that. Actually, the same when you do experiment with adults, you should have very clear rules and very clear feedback and very clear reward. So in this case, the reward was very simple. So you show them their score, and you tell them, look, this other group did that. It's totally tricky, but but it's working. It's working. And so when Katja changed that, then it was finally working for most of the group. Okay, these are the results. So you see, you get again this nonlinear characteristic. So basically, it looks like children from 5 have haptic communication. I mean, it's something spontaneous. And now another thing is that, so when you look at the age difference, so the good subjects are the older in general, what is not completely surprising, right? But so we are still analyzing the data, and we have to find out, because we know that children sensory capabilities are changing. So for example, after 5, it seems that it's becoming better, but it's still not as good as 10 or 12. So we will have to find out whether there are some difference, as you see, because the worse subject are the younger. So whether this can be explained just from the sensory properties, or it need to be explained also by a difference in the sensory integration. Something that is interesting also is that you see that basically the better subjects are leading, right? Automatically. So that's something that is interesting. Again, I mean, all this haptic communication is not conscious, right? It's not aware. The people don't realize that they are connected, but it's coming automatically that if you are better, you tend to lead. Okay, something related. So studies that we did. So you have this father, and the father is, okay, so wants the daughter to learn. And should he be very rigid to guide the bicycle well? Or should he be more compliant, so relaxing the muscle in a way that he can sense better where it is going? And so the question is whether we would change, or we could change the muscle activation to rigidify the limb or not in this. So the same task as before, same interface actually, and you have visual noise, so that sometimes one has sharp target and the other has fuzzy target. And then you want, so why do we do that? Because then the one with a fuzzy target will be less good. And that's exactly what we want to understand. So we want to understand what happens when one is less good than the other. So all possible combination. So one fuzzy, the other fuzzy, the two fuzzy, no one fuzzy. And yeah, so you see this task. So this is like the two-dove task before, just in 1 degree of freedom. Actually, people did experiment also in 3 degrees of freedom with conventional robot. You have exactly the same haptic communication characteristic. So they are separated visually, also phonically. They should not speak together. Also, so I don't think it would change much, to be honest. So we did some experiment where you see the target of the other. It doesn't, you see the cursor of the other. It doesn't seem to change much. Okay, so let's look at performance. So the tracking error, right? So we see that when you are solo, so it's decreasing, and then you have the different condition, and then you have a solo period, and you have the same level, right? So it seems that at this point the performance are constant, right? Okay, then so we look at these different conditions, and we see that, of course, so when there is more noise, so this is I'm fuzzy and the partner is sharp. So when I'm fuzzy, then of course there is more error. And when the two are fuzzy, even more. Logical, right? Now we look at muscle co-contraction. So the great thing of our interface is that it is only one DOF, so you can measure muscle activation. So you can always measure muscle activation, but in this case, it is especially favorable for analysis. So you have co-contractions, that is rigidity of the limb, basically, and you have reciprocal activation, that is basically the force, the torque, right? So very simple analysis. And so what do we see? We see that muscle activation is decreasing. What is evidence of learning? It always is like that. When you have learning, you have a decrease of muscle activation in general. Then what we see is that, so when I'm sharp and the other is fuzzy, then I rigidify my arm, right? And that's something a bit strange, right? Okay, so I'm sharp and the partner is fuzzy. So the partner is fuzzy, meaning that it makes noise in the interaction, right? So we thought, okay, so if there is noise in the interaction, I would probably relax to filter this noise out, right? But in fact, the converse is happening. So when I'm sharp, so the partner is fuzzy, I co-contract, I rigidify my limb. So what could be the reason for that? So yeah, so you have analysis again. Then if we look at a mechanical model and we assume that I have a motion plan, right? Okay, so this is my hand, and I have a motion plan, let's say here. And the great thing is, okay, so if I have a motion plan, then I'm connected to this motion plan through my muscle elasticity, right? So it's like if I have a spring here. So I have a spring between my hand and my motion plan. And the great thing is that I can change the stiffness of this spring. When I co-contract, then you know that. So when muscle activity is increasing, the muscle is becoming more rigid. That's the first property of muscle, right? And then it makes that I can co-contract and change the spring to my motion plan, okay? And then it makes sense. So then if I have very good information, then I should rigidify because I can trust this information well. On the other hand, if I don't have good information, I should relax because I should trust more the partners, right? So I can optimally combine my visual information with the haptic information from the partner, basically, in a way to have a better sensing. And that's something that can be modeled mathematically. So for example, in that way, so what Xiao Xiao did, So you can have prediction error with maximum likelihood. And then the thing is that you can change how close you are from your motion plan, right? So you can change that. So you can change that to make this small. And you have also a term for the energy because you don't want to increase co-contraction forever. So you want to tend to decrease. And so with this minimization of prediction error and minimization of energy, then you can actually predict the behavior, right? So you can predict the data, and it makes that if you have arbitrary noise, so your own noise of the partner, okay, so I know, so it will be here, right, for example. And the other thing is that after that, okay, so this is between humans, right? This is a model, but we can we use that to make that a robot is interacting with the human way, right? So we make that the robot is changing its stiffness according to the relative performance of the human and the robot. Okay, and that's something that Xiao did, and we see, so when we do experiments, so we make this automatic adaptation of stiffness of the robot, and that's an experiment that one person in this room is continuing. And but we had preliminary evidence in 1 degree of freedom that it's improving the performance of the robot relatively to a rigid controller. And actually, it also is improving the performance of the human in the sense that, so what is a cost function of a human? You take error and effort, right? Effort from the muscle activity and error from the tracking error. And then we see that it's also, so it is improving for the human and also improving for the robot. So it's interesting that you can try to understand this human strategy and then transpose to the robot and get a similar effect when the human is interacting with the robot as they would do with a human. A very recent experiment, so that was done by collaborators in Chicago. So they want to do rehabilitation, so human-human rehabilitation, and they want to do for the ankle. Okay, and then they connected people with ankle. And then the question is, of course, whether it is working when you connect ankle. So it's low wheeling, right? It's different. So you have longer delay, for example, than to the arm and other characteristic. And so Matthew, he compared so human connected with ankle and also human connected with the wrist. Okay, and same experiment as we did before, all the same. And okay, so basically they found the same characteristics. So you win with a better partner, and you also win, or at least do not lose, with a worse partner. And whether it is for the wrist or the ankle, it doesn't matter. So the same effect. Now something interesting. When you look at the co-contraction, so this is what we had for the wrist, right? So they confirm what we found, but for the ankle, it doesn't work. So for the wrist, you automatically change the co-contraction to improve the haptic communication, but for the ankle, you do not. And why, we don't actually know, but it may be that, so you know that, so when to keep stable, you would think, okay, so I use the ankle for contraction, right? I use because it can stabilize me. And of course, it's an unstable situation. However, this doesn't work because the muscles are not strong enough to stabilize. And then it is known that for stability, people do not use co-contraction of the muscle, but they use more what we call long delay reflexes. And so it's possible that because people use long delay reflexes for the ankle rather than an impedance strategy, they are not able, or they do not use an impedance strategy here. Okay, so it's all about haptic communication. So let's summarize. So humans exchange haptic information during contact. They understand that what they feel with the hand or with the foot is the same that what they see. And they make a model of the partner, and they do all that in an unaware way. So it's not something that you can avoid, right? It's not something that you can discontinue even if you want. It's something that is happening automatically. They also adapt muscle co-contraction to improve haptic perception, at least for upper limb. And the bigger group, the better. And now let's look at what it means in terms of communication. So if we compare to people speaking together, so people cannot, or should not speak at the same time, right? I mean, when people speak at the same time, it's not really communication because you cannot understand what the other wants, and so you do not win in language communication, in verbal communication. Now, in haptics, you have to be at the same times all the time, and still, so the brain has a way to deal with that. It's not to say that haptic communication is better than language. It's different. It's better for something, it's worse for other things, right? But it's fundamentally a different way of communicating. And now, so I wanted to show you this. So it's a paper that we will look at that is recent. So you have together, and so it's communication with many actors, right? And of course, the question is whether this is happening randomly or whether there is some connection. And actually, the authors of this paper have also done the same experiment with humans. So anyway, so it's not really related, but I like, yeah, so you. Now, how we can use this knowledge? So haptic communication for human robots, right? So personally, I'm not sure I will want to do that with a humanoid robot because I don't especially like humanoid robots, but they are not only humanoid robots, right? So you have, for example, so I have this vision of human working with mobile robot, and normally you would move the table with your colleague, but if one colleague is not in, then there is some robot around, then you take the robot and you communicate the same way. You don't even notice that you do this with a robot. So that would be the vision. Anyway, so let's look for another thing for a bit less ambitious, but also useful for teleoperations. So you consider the robot and the human as agent. And what is an agent? It's something that has actuation, sensing, motion planning, some intelligence, and communication ability, right? That's what we do. And so let's see what we can do for teleoperation. So the idea is always the same, that so the robot is an agent, and the robot will try to model the human, and then can modulate its action optimally, or could even conversely compete or try to make that human is failing. But anyway, it will use some intelligence to understand what the human is doing and to make with or against. So The key is that, so from the interaction force, we extract the target of the human. So the robot is extracting the target of the human, and then it can use for control, for example, here. So so this is for prediction. So for example, we can use it with a well-designed Kalman filter. Now, so you see how it can be used. So you have combination. So the robot has a task. So this is the target of the robot. So the task is given to the robot. So the task is to move on a circle, right? And the robot knows also, oh, okay, so I should not enter this area because it's dangerous. There's some brain or some dangerous area. I should not go there. And then, so this is the task of the robot. And the robot is also finding out the target of the human, so what the human want to do, and then combining. And combining with this lambda parameter. And so this is an experiment. So you see in pink, this is the prediction of the human target, right? And we see that the combination makes that you do not enter this dangerous area, never. And so how do you modulate this parameter? So in this case, for example, this parameter will be the distance to the wall. Right? So if you come too close, then it should go, yeah, I'm sorry, I have to change. It should be between 0 and 1, yeah, whatever. Okay, so some experiment of teleoperation again. So you have a two sheets, so you see this is teleoperating this, and you see you have kind of rigid connection, right? So is that really rigid? No, it's totally compliant. So that's the thing. So because we can detect, so this one is detecting the motion intention of this one, so it can know the motion intention, but use an arbitrary stiffness, so make something very compliant or very rigid, independent on the motion plan. And we can see that. So this is an experiment. So this is the traditional teleoperation strategy. You see that when you have low stiffness, it doesn't work, right? It really doesn't work. This is the state of the art. This is our strategy. So you see that it's following well, even with the same very low stiffness. Now, with the state-of-the-art strategy, if you want to somehow follow, you have to make the stiffness higher. And still, it's not perfect, but it's somehow okay. Now, if you take this middle value of stiffness, then and you want to interact with a fragile environment like this, then it's not very successful, right? And now, because with our strategy, we can use much more compliant behavior, you see that it's okay to interact with the environment. And that's something that you can use, for example, for micro robot, where everything is very fragile, right? So this is for polishing the state-of-the-art strategy. You see that it's okay, but not perfect. With our strategy, it seems that it's following better what you want. Yeah, now something that is really important for industry, so assembly task, right? So this is the state of the art. You see that it's not obvious. And with our strategy, because you use a motion plan, right? You transfer the motion plan, and then it's working much more easily. So we see this. So this is this assembly task with the state-of-the-art controller. So for example, this is orientation. And you see, so the dashed line is what the operator would like to do. And you see that the robot is not following at all, right? And when you use the motion plan, you see that conversely, so the robot is following well what the operator wants. And so you enter the hole relatively fast. So you can see this with 8 subjects. So you see that the performance is admissible and actually good with when you use a motion plan. So our strategy, and it's not sufficient for the state-of-the-art patient strategy. Okay, and now, so this is how you can exchange sensor information between a robot and a human by exchanging the motion plan, right? And that's important, this exchange at the level of motion plan, because, so for example, the same for BCI, if you pass just a position, it's not very successful. If you pass a motion plan, you can get better results. So another thing, so we looked at how human and robots can fundamentally interact. So depending on the nature of the task, so if the task is divisible, so in this case where this guy is controlling this movement and the machine is controlling that movement, then these co-activities, they do not have to communicate. You have the impression they work together, but they do not. So each one, the robot or the human, is doing their task, and it looks like they work together because of how the tasks are structured, but they don't. Now, if the task is together, then you can antagonize, so this is competition, or you can work together, or you can assist completely, so master-slave, so the robot should provide the energy that the human wants. So the robot could die, it doesn't matter. The important thing is that the human get assistance. And you can have education where you want to assist, but not too much. Because so you want to assist just what is needed, because if you assist too much, the student become passive. And so what we assumed in 2012, so we assumed, okay, so these are these behaviors, and we can define them to cost function. So I can decide whether I have master slave or another thing. I can specify with a cost function. And so what we have to do is that the robot has to identify the cost function of the human and then can play with that. So with each cost function and the cost function of the human. So this is game theory, right? I mean, game theory, so you have so game theory, you have that so you have that the robot knows about the human cost function and knows about its cost function, and it considering both, right? This is game theory. You have a model of the partner and you consider both to generate your command. So you have the robot and the humans, they have to move the common object. You can linearize that. So now you have this linear system, so you have to follow this target. So this is a state. And if you want to minimize the error and minimize the efforts, then you have typical LQR solution, right? So this is if the robot is not considering the human. Now, game theory, so the robot is considering a cost function for itself and a cost function for the human, okay? And so we have something similar to LQR, but in this case, we have Kaplan equation. So this is interesting because the matrix of the system for the robot is the matrix of the system minus the human, okay? And conversely, the matrix of the human model is the matrix of the model minus the robot, right? So you have kind of you have coupling between this human model and this robot model. And of course, I mean, so what I showed you is game theory. It's not something that we invented, but strangely, nobody had done that. The robot has to identify the human. In game theory, people were assuming that the agent have just knowledge about the partner. But if you have a human and the robot cannot know the human. So the robot has to learn the motion control of the human. And that's what we did. So we developed an algorithm to identify the motion control of the human, and then that's the behavior that we got. So okay, so you have this human making experiment with a robot, and the human is playing different role. So in red it's making no interaction, so something like that, and then the robot understands there is no human and providing the effort. This is the red line, right? So this is for this movement, just back and forth. Now, if we ask a human to play a weak arm, so basically you take the handle, but you don't do anything, you are passive, then the robot understands that the human is weak and increasing the effort, okay, automatically. And now, if the human can do the movement, then the robot understands that. And then the robot is decreasing assistance even to come to compete, so to break the movement. So basically, so the robot is taking over the motion control of the human and considering and adapting according to the plan, right? According to what was planned. Now, there is okay, so the robot can identify the human and adapt. Now, another question is, so if the robot is imposing a relationship, will the human follow? And this is something that is important. So for example, if you want that the robot is making training of the human, the robot want to make that the human is becoming more and more engaged, for example. Then the robot will try to impose a relationship, and we don't know whether the human is following that. So so you have this cost function for the robot. So the robot is using a cost function where you have the human efforts and the robot efforts, right? And you have this parameter here that can tune how much the robot will give and how much the human should give. And so, for example, if this parameter is 0, then you have competition, right? The robot would go against the human. Conversely, if this parameter is 1, then so the robot would provide the whole effort. And the question is, okay, so the robot is providing the whole effort, but will the human understand that and become passive or not? You can have also collaboration, of course, and you can have education. So typically you would start with full assistance, and gradually you would decrease assistance so that the trainee is becoming more and more able to do the task by themselves. Okay. Now the question is, okay, so in the group of Bastien Burdet, they did an experiment, so using this cost function, and then what they found is if the robot is imposing a relationship, so with this parameter, then we see that so the robot, we see that the human is changing its contribution, right? So the robot is deciding, I want to assist you completely, and then the human is understanding and not fighting, for example. So this is the converse as we had before. Before we had the robot can understand what the human is doing and adapting. Now we have the converse. The robot is imposing something, and we see that the human is following, is implementing this desired relationship. And so, yeah, I come to the summary of what we try to do. So you have basically human robot or human as two agents. Okay, with sensing and motion planning abilities. And we use differential game theory as a tool to describe, analyze, and generate the motor behavior. So you have this sensory interaction where the robot is inferring what the human wants to do and combining with its task. And the robot is also deciding on a relationship with a human. And so this is the sensory exchange, and this is the motor exchange between the human and the robot. And we have seen that the robot can adapt to a motor condition, and the robot can also induce specific roles in the human, sorry. And okay, so the summary of human-robot interaction. So this is what you have in traditional human-robot interaction. So either you have a kind of master-slave relationship where whether for teleoperation or for assistance with this exoskeleton, so the robot is reproducing exactly what the human wants. Conversely, you have coactivity where the robot is doing something, the human is doing another thing, and it happens that it is coordinated because of the task, for example. So in this case, the robot is doing exactly all what the human wants. In this case, the robot doesn't care about the human. And what we want is something different where the robot is considering what the human wants and adapting its behavior correspondingly. So this is useful for training, for example, in rehabilitation, robot-assisted rehabilitation. This can be a strategy for shared driving, where so you have the car, and the car has its sensors. So it can be considered as an agent, and you have the human driver, and they communicate over the drive wheel, right? They communicate mechanically over the drive wheel, and then you can make that the car would see something with its sensors that the human does not, and then the human would feel with the drive wheel and consider that. This may avoid accidents that we heard about where the car is not seeing something that the human could see. And you can have competition where the robot would compete against a human. We don't know yet actually how to use that. But in any case, so this behavior rely on the robot understanding what the human wants and adapt to the emotion. And okay, so let's come back to this question. So is that better to have three hands or to work with a human partner? Is that better to have three hands or to work with a human partner? So it's better, I mean, you can play with both, right? So either you have sensory, so you get the sensor information from a robot, and it can augment your information and your knowledge of the task and what you can do. Or you can sometimes use a third arm, for example, for surgeon to do all by yourself. And actually, you can have both, right? So, in fact, if If you have a surgical robot that is kind of third arm, the surgical robot will provide you sensor information that is complementary to your sensor information. That's all for my presentation. If you have questions, I'm available.